go ahead and start. Okay. You got it now? Okay, so reminder that we do have class tomorrow. It is considered Friday instruction. So we'll actually have a quiz tomorrow, our last quiz since it's our last in-person class. So that's going to cover chapters 12 and most of 13, because we'll complete most of 13 today. The other thing it means is that I'll have my Friday office hours tomorrow as opposed to my Tuesday office hours. And the Friday office hours are from 12 to 1. So if you're planning on coming in for office hours, make sure you note that it's the Friday office hours. So the next two chapters of the book are different from the others in that they involve analytical techniques that are used to determine the structures of organic molecules. And there are three main analytical techniques that we use. We use mass spectrometry, IR spectroscopy, and NMR spectroscopy. And NMR spectroscopy is the one that gives us the most information, although all three are valuable. So NMR spectroscopy gets its own chapter, and we're barely going to scratch the surface of what you can do with NMR spectroscopy. Those of you who are chem majors, I strongly encourage you to take Chem 455 next year, which is a class, and a big bulk of the class is delving deeper into NMR spectroscopy than what we do in this class. So it's a very, very fun and interesting class. But then in chapter 13, we're going to look at mass spectrometry and IR spectroscopy. The data we obtain from those techniques are more limited, but still valuable in helping us determine the structures of organic molecules. So today, we'll cover mass spectrometry, and we'll cover most of IR spectroscopy, but we'll finish IR spectroscopy and start chapter 14 tomorrow in class. So what we learn from mass spectrometry is the molecular weight of the compound that we're analyzing. Specifically, the mass to charge ratio. We'll tell you what that is in a moment. But what we have to do first is ionize our molecules. In order to analyze them by mass spectrometry, we have to ionize them, okay? So this shows us a diagram of a type of mass spectrometry known as electron impact ionization. Or EI, and that involves the use of a high energy electron beam. Which is 70 electron volts. That's a unit of energy used to measure electrons. And that comes out to be about 1,600 kilocalories per mole. That's a ton of energy, okay? So the ionization potential of most organic molecules is about 15 electron volts, meaning that's the amount of energy it takes to rip an electron off of a molecule. So this energy is more than sufficient to rip an electron off of any organic molecule. So we generate a high energy electron beam. This schematic diagram here shows us the electron beam is coming from this coil, or I guess in this diagram, it's coming from down here. The sample is introduced to a chamber. The electron beam knocks an electron off of the atoms, forming ions. An electric field accelerates those particles into a magnetic field, and the magnetic field causes the charged particles to bend. Okay, the path of those particles is bent towards the magnet. And so the amount of bend in the path is related to what is known as the mass to charge ratio, which is referred to as M over Z. M is the mass, Z is the charge. Z is usually 1, but as we'll see in some mass spectrometry, it is not 1, it is greater than 1. In most cases it is, but not always. So the particles with the higher mass to charge ratio are bent less by the magnetic field. So they're going to hit towards the right side of this detector. The particles with a lower mass to charge ratio, their path is going to be bent more. They're going to be detected at the right side of this detector. So where the particles hit the detector depends on that mass to charge ratio. So that's how we figure out what it is. And then when Z is 1 and we've lost a single electron from a molecule, that's going to be what's known as the molecular ion. Okay? The molecular ion is what we're looking for. That's going to have the same molecular weight as our compound, right? Because the mass of a single electron is pretty negligible. Now, the amount of energy that we're using is much greater than what is needed to just knock off a single electron. In fact, it's enough energy that we can cleave sigma bonds in our molecule of interest. The bond dissociation energies on the electron volt scale are usually in the range of 3 to 10 electron volts. So we've got plenty of energy available to cleave sigma bonds. So we also end up with fragments. We see fragmentation in mass spectrometry. And we don't really worry about fragmentation as much in organic chemistry as we used to, because the data about structures that you can gain from fragmentation is now more easily obtained using NMR spectroscopy. But we'll show you when we show you a spectrum in a couple minutes what we mean about the fragmentation and the fragments that are produced. Here's another schematic of this EI mass spectrometer. We're not going to focus on this one as much, except there's one key bit of information here at the bottom. This method requires you to be able to vaporize your analyte, or the molecule you are analyzing. And so the molecular weight has to be less than 1,000. Molecules with higher molecular weights, you can't really vaporize them. Usually it works best for molecules of a 500 molecular weight or lower. All right, here we have a live action animation of electron ionization. So here we have this hot filament that's spitting off these high energy electrons. And then here we have our molecule that we're analyzing inside this column that's being introduced into this chamber. And as it flows into the chamber, it's then going to get hit by one of these high energy electrons, which will knock an electron off and turn it into an ion that then gets accelerated into the mass analyzer. So here we go, ionization, and now it gets analyzed, okay? If you want to see that again, ionization, and now it's getting analyzed, okay? This figure is available on Learning Suite, so you can play with it at home if you would like to. Here's a mass spectrum. On the x-axis, we have m over z, or mass to charge ratio. And as I mentioned, z is usually 1. So this typically tells you the masses of those ions that are being detected. On the y-axis, we have relative abundance. We take the largest peak in the spectrum, which is known as the base peak, and set that to 100%. And the abundance of all the other peaks are calculated relative to that. The base peak is not going to be the molecular ion because of the fragmentation that occurs. Okay, so the fragments are going to be taller in EI mass spectrometry than the molecular ion. In this case, our molecular ion is right here. The way you identify the molecular ion is you'll find a cluster of peaks to the right end of your spectrum, and the tallest peak in that cluster is going to be your molecular ion. Okay, so this particular compound has a mass to charge ratio of 86. It actually corresponds to hexane. The base peak is 57. If you subtract 57 from 86, you get 29. That corresponds to C2H5 or an ethyl group. So what's happened to generate this fragment is we've cleaved the carbon-carbon bond here, an ethyl group has come off, and this is what remains. Okay? If we look here at 71, that's 15 less than our molecular ion. That tells us that a methyl group has cleaved off to give us that fragment. So that's the sort of analysis we used to do with fragmentation. Sometimes it's still done on standardized exams, but as you can see, it's really easy. All it requires is a periodic table and an ability to do arithmetic. So we're not really going to spend any time on that. But there's an interesting feature here. Here's our molecular ion. We have a peak 1 unit higher than our molecular ion. Why? Okay. That would be half, right? So if you had a Z of 2, you'd be sitting down at 43. Okay, yes. An isotope, yes. So on the periodic table, we have these atomic masses that are weighted averages of the isotopes for those atoms, right? The most abundant isotope gets the most weight, and less abundant isotopes get decreasing weight when calculating these weighted averages. But there's no such thing as an average atom. You either have one isotope or you have another. So with carbon, carbon 12 is our most abundant isotope. But we have carbon 13 with a 1.1% relative abundance. So roughly 1 out of every 100 carbon atoms is going to be a carbon 13 atom. So if you have 6 carbons in your molecule, you have essentially a 6% chance of having 1 carbon 13 atom in that molecule. So this M+1 peak that's shorter than the molecular ion is coming from the fraction of molecules in the sample that had a C13 atom present, okay? So with larger molecules, the relative abundance of that M+1 peak will get higher. You get up to 50 carbons, and now you're going to have roughly a 50% chance of having a C13 atom in your molecule, okay? So that's why we have an M+1 peak in the spectrum. Any questions? Okay, so let's talk about some features of mass spectrometry that that are very helpful to us, that give us useful information. The first one is what we will call the nitrogen rule. Okay, the nitrogen rule is very handy. It works for molecules that only have carbon, hydrogen, oxygen, nitrogen, sulfur, or halogens. Okay, that's actually most organic molecules. The only common element present that's not up here is phosphorus. If you have phosphorus present in your molecule, this does not apply. But as long as you don't have phosphorus and you don't have any other exotic elements, if you have, well, we'll start with even, sorry. If you have an even molecular weight, that tells you you either have no nitrogen atoms or an even number of nitrogen atoms. Okay, sorry. If you have an odd molecular weight, that tells you you have an odd number of nitrogen atoms in your molecular formula, which would mean you have to have at least one nitrogen. Okay, so odd molecular weight tells you that you have at least one nitrogen in your molecule. You might wonder, how can this be? How can it be so simple? Well, it relates to the atomic masses of these elements and the number of valences they have, or the number of bonds that they form. Nitrogen has an odd molecular weight, an even molecular weight, and an odd number of valences. Right? It's the only one that has that. Okay? So because of that, if you end up with an odd molecular weight, you have to have a nitrogen if these are the only elements you have in your compound. Okay? Now, most of the molecules we'll be looking at are going to be relatively small, relatively simple. They're usually going to have either 0 nitrogens or 1 nitrogen. Okay? So in most cases, if you're working a problem and you have an even molecular weight, it's very unlikely you would have a nitrogen in that molecule, because the likelihood of having 2 nitrogens is not going to be very strong. And if you have an odd molecular weight, you probably have 1 nitrogen instead of having 3 or 5. Okay. Any questions about the nitrogen rule? All right. So this sample problem that we have shows us how we would use mass spectrometry data to come up with possible molecular formulas of a compound. So this is coordinated with that previous spectrum. The molecular ion was at 86 in the previous spectrum. So how would we come up with possible molecular formulas for a molecular weight of 86? The first thing we do is divide 86 by 12 to figure out the maximum number of carbons that we could have. In this case, we get 7 remainder 2, C7H2, and that first formula that you get is probably going to be a nonsense formula, right? How many degrees of unsaturation are there in this formula? What's the maximum number of hydrogens you can have with 7 carbons? 16. If we have 2, that's how many degrees of unsaturation? That's 7, right? 7 degrees of unsaturation. You're not going to have 7 degrees of unsaturation with only 7 carbons, okay? So how do we get from this to a reasonable formula? Well, you subtract a carbon and add 12 hydrogens in its place, right? You can remove elements and add a number of elements that's going to have an equivalent mass. So we take out 1 carbon, add 12 hydrogens. Now we get C6H14. Is that a reasonable formula? Indeed, right? That's hexane. That's what we had on the previous slide. But if we didn't know it was hexane and we were looking at other possibilities, then we could start to add oxygens in. Oxygen has an atomic mass of 16, and so we would need to take out a CH4 in order to put it in oxygen. We take out CH4 from this, we get C5H10O. How many degrees of unsaturation? So 5 carbons, what would be the maximum number of hydrogens? 12. So 1 degree of unsaturation. So is that a reasonable formula? Absolutely. We could have 1 double bond or we could have 1 ring. Then we can try again. Take out CH4, add an oxygen, C4H6O2. How many degrees of unsaturation are there in this formula? There's 2. So this is also a reasonable formula. We could have 2 double bonds, or we could have a double bond in a ring, okay? So this is the process we go through to generate possible molecular formulas. You could, if you really wanted to, you could stick 2 nitrogens in this case, because it's even, so it would have to be 2. And a nitrogen is 14, so you would have to replace CH2 to put a nitrogen in your formula, okay? And then you would use the IR data and the NMR data to distinguish between the possible molecular formulas that you have, okay? Any questions? All right, so the next useful bit of information we get from mass spectrometry deals with chlorine and bromine. Chlorine and bromine are unique in that they have 2 isotopes that are relatively abundant. So with chlorine, chlorine 35 is the most abundant isotope, but chlorine 37 is second, and the ratio between these 2 isotopes is 3:1. So when you encounter a molecular ion, and then you encounter a peak at M+2 that is 1/3 the height of the molecular ion, you know that you have a chlorine in your molecule. So here's an example. This is isopropyl chloride. You would calculate the what we call the exact mass by using the most abundant isotope of each atom. So we would use chlorine 35 and get an exact mass of 78. So we'd say this is our molecular ion, this is our M+2 peak, and with chlorine we would have a ratio of 3:1. So if we see that, we know we have a chlorine in our molecule. We've got to put a chlorine in our molecular formula. So that's very useful. Bromine bromine 79 and bromine 81 are equally abundant. So if we have a 1-to-1 ratio between the M peak and the M plus 2 peak, then we know we have a bromine in the molecule. So the next mass spectrum we have is isopropyl bromide, and here we see the M peak and the M plus 2 peak. Okay, so that's very helpful in allowing us to see the presence of bromine or chlorine in our molecules. Any questions? Yes? No? Okay, other questions? Say that again, I'm sorry. Yeah, so conventionally, when you have, so with the chlorine, it's the one that's more abundant. With the bromine, conventionally, you say the molecular ion is the one that comes from bromine 79, and the one that's 2 units higher is just the M plus 2 peak. The picture says 2 molecular ions. It's easier to say that you have a molecular ion and an M plus 2 peak. So I would use slightly different language than what they have up here. Let's see. Oh, yes. The other thing I was going to say is that you can have multiple halogens in a molecule, and then you're going to get a more complicated pattern. You're going to have a combination of an M peak, an M plus 2 peak, and an M plus 4 peak if you had 2 chlorines, 2 bromines, or a bromine and a chlorine. Okay. So we have software that would calculate the pattern of those peaks that you would expect to see. It's called ChemDraw. ChemDraw is used to draw organic molecules, and all chem majors have access to it. We have it in the computer lab in the Nichols building, and you can also download it on your own computers following instructions on the chemistry department website. And so that's the software that I use and that anybody who does organic chemistry uses to draw organic molecules. And it has a feature that allows you to calculate the mass spectrum that you would expect to observe for a given molecular formula. So if you had a crazy looking pattern down here, you could try to figure out what combination of chlorines and bromines would match that pattern by calculating it out. Okay, any questions? So let's talk about some special types of mass spectrometry. HRMS stands for high resolution mass spectrometry. The standard version, which uses less expensive instruments, gives you accuracy to a single atomic mass unit. And that's good enough for allowing you to determine multiple possible formulas. But if you could determine that molecular ion down to 4 or 5 decimal places, then you'd get to the point where there'd only be one formula that would fit. And so a high resolution mass spectrometer will do that. Here's some exact masses of common isotopes. You see that carbon 12 is the one that we set at a whole number, and the others are slightly different. Fortunately, we have a couple of instruments that do high resolution mass spectrometry here at BYU, so our research students are able to do this and don't have to calculate multiple possible formulas the way you guys do on tests and homework problems. And then another interesting application of mass spectrometry is this one shown here schematically. This is called GCMS, where the GC stands for gas chromatography. So this is coupling a separations method with mass spectrometry. So this allows you to analyze, this allows you to separate the components of a mixture and analyze each of those components separately in a mass spectrometer. And this used to be used in airport security. It's faded away. Now they use those I think they're microwave scanners, but those scanners that look to see if you're hiding anything. But they used to have you, this was back in the 2000s, I think, you would go into this little booth, similar to the one where they have the scanner now. but you'd stand there and then you'd hear a little puff of air, and they'd have you stand there for a while, and then you would walk out. Has anybody ever gone through one of those before? Or are you too young? Okay. So what they were doing is that puff of air was disturbing the residual chemicals on your skin and your clothing. And then they would have some sort of a vacuum device that would suck that into a gas chromatograph and then separate any of those chemicals into their individual components. And then you would analyze them, analyze each of those individual components using mass spectrometry. So what they were looking for was residues of bomb-making chemicals. Mass spectrometry is incredibly sensitive, so all they need is a teeny tiny amount to be able to detect it. So if you'd been making bombs and then you were getting on an airplane, you would certainly have residues from those chemicals on your skin. If you didn't, even if you changed your clothes, you'd still have some of it on your skin, and it would probably get picked up. You'd have a complicated mixture of chemicals, and they would be separated into their individual components by the gas chromatograph. And those individual components would be fed into the mass spectrometer as they came off the gas chromatograph. They would be ionized, and as long as you had 70 electron volts, as long as you have a consistent energy in your electron beam, you're going to get a consistent fragmentation pattern of a specific molecule. So if you had a specific explosive, if you had TNT on your skin, it would give a very consistent fragmentation pattern as well as its characteristic molecular ion. You would store the mass spectra in the computer that's running the instrument of the compounds you were interested in looking for. And if you found any hits, then the person at airport security would be alerted to pull you aside and question you, as well as look through your luggage. Okay. This technique is also used for drug testing. We talked about steroids and performance-enhancing drugs in Chapter 12 last week. But some of the molecules of interest there are higher molecular weight. GC requires you to be able to vaporize your molecules of interest. If they are too high in molecular weight and have too high of a boiling point, then you can use HPLC or liquid chromatography, LCMS. It's not as fast as the GCMS, but it can be used for drug testing. It's not really used in airport security applications, but it is used for drug testing. Okay? Any questions about these techniques? Okay. So the next one we'll talk about is called, we only want to raise one of these boards, sorry. It's called ESI, or electrospray ionization. So one of the previous schematics we showed you of an electron impact mass spectrometer showed you that it works best with low molecular weight compounds. You have to be able to vaporize your analyte molecule in order to use EI. So if you have large molecules, such as proteins, you're not going to be able to vaporize a protein to study it by EI mass spec. But you can use electrospray ionization. This was developed by multiple people, but a man named John Fenn was the key player. And because of the wide utility of this method, he won the Nobel Prize in Chemistry in 2002. So this allows you to take a solution of your compound and introduce that solution into the mass spectrometer. So you can ionize much larger molecules than you would be able to ionize by EI, where it has to be able to become a gas. So what happens is you have a syringe pump, you have this needle that has a very high potential on it that spits out these charged droplets. So you have your solution, and those droplets are charged. Then that goes through this area with a drying gas, nitrogen typically. And so the nitrogen is going to evaporate some of your solvent molecules. So your charged droplets are going to get smaller and smaller, but the charge is still there. And so you get you decrease the volume of that charged droplet, and pretty soon you start to get this very strong electrostatic repulsion, and you get what's known as a Coulombic explosion. Okay. Now, I'm not an analytical or a physical chemist. I don't know all the details about Coulombic explosion, but I think it's a pretty cool sounding term. But what I know that it does is that the energy from that Coulombic explosion that comes from shrinking the volume of those particles is what causes the ionization of the molecules. That's what produces the energy that knocks electrons off of the molecules. And the good thing about this is it can knock multiple electrons off of large molecules, and you can get multiply charged ions. So that allows you to detect molecules up to around 200,000 in terms of their molecular weight. And the way we can detect them on our detector is they would have multiple charges. They would be dications, trications, and so forth. And we would be able to use, based on the patterns of peaks in the spectrum, we have software that could tell us what those charges are in those peaks, and in the end tell us what the molecular weight is of our compound of interest. Okay, so that's what electrospray ionization does. It allows us to ionize proteins and study proteins. We have several research groups at BYU that study proteins by mass spectrometry. So they use electrospray ionization in many cases. We also use it to analyze some of our larger molecular weight organic molecules. Question, Claire? Yes. They probably have some charge because most proteins have side chains that have charges at neutral pH. But then this needle here with this high potential causes the droplets themselves to be charged, and then as those droplets shrink down, then boom, you have your Coulombic explosion that causes ionization. Yes. Yeah, you're starting to get beyond the limit of my understanding of how the technique works. So we'll just stop there, I guess, in terms of describing how the technique works. But we have plenty of people in the department who are experts in mass spectrometry. Dr. Austin, Dr. J.C. Price, Dr. Ryan Kelly, they all use mass spectrometry in their work. So there's plenty of people you can consult, Dr. Dearden, who know more about the specifics of these instruments than me. I just know how to interpret the data that we get from them. All right. So any other general questions on mass spectrometry? Okay, so before we go into IR spectroscopy, we're going to talk a little bit about electromagnetic radiation, because electromagnetic radiation is the basis of IR spectroscopy and NMR spectroscopy. You'll notice there's two terms, spectroscopy and spectrometry. Anyone who is a spectroscopist will tell you that spectroscopy involves hitting your molecule with electromagnetic radiation. When it's not electromagnetic radiation, you have to call it spectrometry. So in mass spectrometry, we're not using electromagnetic radiation. We're ionizing our molecules, either using electron beams or charged droplets or what have you. But in IR and NMR spectroscopy, we're using electromagnetic radiation. So a few terms that we need to understand. Photons. These are terms you've learned in previous classes. What is a photon? Who would like to tell us? Claire. A particle of light, yes. So when you're referring to light as a particle, you would refer to it as a photon. So we'll say it is a particle of electromagnetic radiation with a discrete amount of energy. And that's the key, is that a given photon will have a given amount of energy. Okay? Then we have lambda. What is lambda? That's our wavelength. What do we use to measure lambda? We use nanometers. We can see that up here on our scale. Okay. Nu, that's not a V, that's a Greek letter nu. What does that represent? That represents frequency. And what are our units of frequency? They're hertz, which is inverse seconds. The number of peaks or troughs of your wave that passes a given spot in a second is going to be frequency. So a couple of equations. The speed of light is equal to the wavelength times the frequency. So that equation tells us that frequency and wavelength are inversely proportional. We see that here on this diagram. Wavelength increases from left to right. Frequency increases from right to left. And then our second equation, we're just using these equations qualitatively in this section. E equals h nu. So that tells us that energy is proportional to frequency, meaning that our higher frequency radiation has higher energy. So on here, we see that written here. Gamma rays would be the highest energy radiation, whereas radio waves would be the lowest energy radiation. And what we're talking about in this section is infrared radiation, which is just below visible light in terms of its energy. And then NMR spectroscopy actually uses radio waves, our weakest, our longest wavelength, longest wavelength, lowest frequency radiation. Okay. So this is the basics. Now let's talk about how this applies to organic molecules. So we know that our organic molecules have discrete energy levels. And they have three different types of energy levels. We have electronic energy levels. That's referring to the orbitals. We have molecular orbitals of varying energy, sigma bonds, pi bonds, pi star, sigma star. We have all these different molecular orbitals at different energy levels. So that's what we're referring to as electronic energy levels. We also have vibrational and rotational energy levels. When we say rotational energy levels, we're talking about rotations about sigma bonds, such as a staggered conformation of a molecule versus the eclipsed conformation of the molecule. We're talking about the energy differences between two different chair conformations from ring flipping, a chair versus a boat. So these are all rotational energy levels, which would be different energy levels of molecules that are related by rotation about the bonds. Vibrational energy levels deal with stretching and bending of bonds, which we'll show you in a moment, okay? And then our third type of energy levels are the nuclear spin states. And we will talk about nuclear spin states tomorrow when we talk about NMR spectroscopy, okay? So for a molecule to absorb energy, the energy of the photon that it is absorbing must match exactly the difference in energy between two of its energy levels, okay? So we have a higher energy level, a lower energy level. We have a difference in energy between them, and that must match the frequency based on this equation right here of that photon in order for that light to be absorbed by the molecule, okay? So in IR spectroscopy, we are dealing with vibrational energy levels of molecules. We're dealing with the stretching and bending of bonds. And the difference in energy between those vibrational energy levels is going to be photons in the infrared region. Okay, so we're going to shine infrared light on our molecules, and they're going to change vibrational energy levels. So we can look at a sample spectrum Here's an IR spectrum of 1 propanol. On our x-axis, we have a wave number scale. Wave number, as you see here, that is the frequency scale. So the wave number is represented by nu with a line over the top. That is equal to 1 over lambda, right? So frequency is c over lambda. This is 1 over lambda. So this is a unit of frequency, but it's on a different scale. The units are inverse centimeters. And those units are more convenient. They give us nice whole numbers that work well on the x-axis of our IR spectrum. Okay? And then we have percent transmittance. What happens is we shine a beam of IR radiation through our molecule, and we're detecting how much of each wavelength makes it through. So if we have a high percent transmittance, then most of that made it through, and very little of it was absorbed into our molecule. So where we see absorption, we see a very low percent transmittance. So where we see low percent transmittance, those are the frequencies that were absorbed by our molecule. For some reason, we have the large numbers of wave numbers at the origin, at the left of our x-axis, and the small numbers at the right. Anytime we have something weird in spectroscopy, we can blame it on the physical chemists who came up with the theory behind it. Okay, so the physical chemists are responsible for anything that's odd, that doesn't make sense with spectroscopy. Okay, so these are the higher frequency, higher energy wavelengths down to the left of the spectrum, and the lower energy wavelengths are on the right. Okay, so why are these molecules absorbing IR infrared radiation? Okay, the reason is that by doing so, it causes the bonds to stretch or bend. So if we treat our bonds as weights on the end of a spring, here's our spring, which represents a bond, and then we have the atoms on the ends of the bond. We're familiar with bond lengths, but what we don't realize is that those bond lengths are not static. We can actually stretch our bonds. They can vibrate. And so when we absorb the right amount of energy, our bonds can vibrate or stretch. Okay. We can also have bending at tetrahedral atoms. So if we have a tetrahedral atom, and 2 of the atoms bonded to that are vibrating like this, that's referred to as bending. And a certain amount of energy absorbed by a molecule will cause either stretching or bending. So that's what we're observing. And different types of bonds will stretch or bend at different frequencies. And so the peaks are going to represent different types of bonds. We'll learn this tomorrow in class, but this peak is referring to an OH bond stretching. This is referring to CH bonds stretching. So by learning which types of bonds are present in a molecule, we get information about the functional groups in that molecule. So whereas mass spectrometry gives us information about the molecular weight of the molecule, IR spectroscopy is giving us information about the types of functional groups that are present. So I've told you that these energy levels, there's a very specific difference in energy between those levels. So we would expect very sharp peaks in an IR spectrum, but that's not what we get. We get broad fat peaks. If you're wondering why that's the case, it's because we have several different rotational energy levels overlapping or superimposed on our vibrational energy levels. We have molecules that are in an eclipse conformation, in a gauche conformation, an anti-conformation, a stagger, so we have all these different conformations with slightly different energies, which means that we can actually have a range of absorbances if the molecule is rotating at the same time as absorbing the energy. So that's why these peaks are fatter than we would expect based on what I told you over here. Okay? So why do certain bonds absorb energy in different regions of the IR spectrum? To understand that, we have to understand the physics behind the motion of atoms attached to a spring. Whose law covers the motion of weights on the ends of a spring? Any physics whizzes in the class? Hooke's law. Yes, very good. So Hooke's law, we're going to use wave number instead of frequency because wave number is what we are detecting in the IR spectrum. So the wave number is equal to a constant times the square root of F over m. In Hooke's law, what is F? It's not frequency. It is the force constant. F equals the force constant. And that is a measure of the stiffness of the spring. If we translate that into chemistry terms, that's going to be a measure of the strength of the bond. A stronger bond is going to have a higher value of F. A weaker bond is going to have a smaller value of F. So that's going to be directly proportional to bond strength. So based on Hooke's law, would a stronger bond require higher energy radiation or lower energy radiation to stretch? I'll ask you another question. Is F in the numerator or the denominator? It is in the numerator. So would a stronger bond require more energy or less energy to stretch than a weaker bond? More energy because it's in the numerator of the equation. M is the mass of the weights. And so that's going to be the atomic masses of the atoms that are involved in the bonds. So let's say we have a bond to a hydrogen, our lightest atom. Is that going to require more energy or less energy to stretch than a carbon-carbon bond? More energy because the mass is in the denominator of the equation. So if we have lower atomic mass atoms in the bond, we're going to need higher energy to cause those bonds to vibrate. So Hooke's law is what tells us where, or allows us to predict where the different bonds are going to stretch and bend in the IR spectrum. So based on what we've told you, we're going to skip that, and we're going to get out our iClickers. And we're asking you to look at this molecule and determine which of the three indicated CH bonds will absorb at the highest wave number in the IR spectrum. And you can, for your reference, we still have Hooke's law written on the board. All right, let's try to get our final answers in the next 15, 20 seconds or so. Okay. Any more answers? Going once, going twice. Okay. So these are all carbon-hydrogen bonds. So do we need to worry about the masses of the atoms? No, so all we're focused on is the bond strength. Which bond will absorb at the highest wave number, the strongest bond or the weakest bond? The strongest. So which of those CH bonds is the strongest? C, right? We know sp carbon-hydrogen bonds have higher bond dissociation energies. They're shorter bonds. They're stronger bonds, okay? So we can look at the IR spectrum, and we can divide it into 4 regions based on our understanding of Hooke's law. We see that lighter atoms, bonds to hydrogen, are going to require the most energy to stretch and bend because of the light atom effect in Hooke's law. And then we can find that you'll have an order from right to left of single bonds, double bonds, and triple bonds because stronger bonds are going to vibrate at higher frequencies. Most molecules have lots of different types of single bonds, and so this region called the fingerprint region is usually a mess. We're typically not going to try to interpret that region of the spectrum. It's too difficult to interpret. But these other areas, they're going to have less peaks in them, and so we're going to be able to pick out certain peaks in these regions that are going to give us information about the types of bonds, and by extension, the types of functional groups that are present in the molecule. And we're going to look at those tomorrow at the beginning of class before we jump into chapter 14 and NMR spectroscopy. Please remember to turn in your papers, your summaries and peer reviews if you haven't done so already. And remember, we're going to have a quiz in class tomorrow.